Hello, and good morning, or good afternoon, or good evening, everyone. Welcome to the day third of the Supercomputing Frontier Europe. And my name is Keboku from University of Tsukuba, Japan, and it's my pleasure to chair this session. So today's first session consists of four talks as an invited lecture and the industrial talk. So first speaker is Professor Onur Mutlu from and he's a professor of computer science, information technology, and electrical engineering department at ETH Zurich. And his today's talk is intelligent architectures for intelligent systems. And I will introduce another one. Or is it okay to introduce all of them now? Okay. So the second speaker is Professor Sunita Chandra Sekaran. And she is an assistant professor of Department of Computer and Information Sciences, University of Delaware. And her talk title is Best Practice for Productive Yet Performance Software Development. And third speaker is Dr. Fozan Hosseini. She is the professor, project lead and the technical manager at NAG Limited. And the title is Meet the POPCOE, Getting Insight into HPC Code Behavior. And the last speaker of this session is Santosh Ansumari. He's an associate professor of the Jawaharlal Nehru Center for Advanced Scientific Research towards CFD, and it is a focus talk on India, and his talk is titled as Towards CFD at Extra Scale. So go back to the Professor Onur Mutlu. Are you ready?
Yes, I'm ready. Thank you for the introduction.
Okay, so you have in total 15 minutes, including the Q&A. So please keep your time. So please go ahead.
Okay, great. Well, thanks everyone. Welcome all over the world. I'm going to talk about intelligent architectures for intelligent systems today, describing some computer architecture and platform challenges that we would like to solve to make systems much more energy efficient and also high performance at the same time. I think this goes without saying today that computing today is bottlenecked by data, and data is really key for many important applications. Certainly, the applications dealt by supercomputing, AI, ML, genomics, important workloads are all data intensive. They require rapid and efficient processing of large amounts of data. And on top of this, data is increasing. Today, we can generate much more data than we can process, which has enabled, in part, the machine learning revolution that we're experiencing today. But we know that many of the workloads that we design and that we work with today are limited by data. You can see some examples of them over here. Data becomes a performance energy bottleneck in them. And also some workloads on the mobile end or mobile plus server end are also very much bottlenecked by data in terms of performance and energy and reliability and other issues as well, as we will discuss. And data is key for future workloads because data is increasing. I take an example from genomics over here. Today, we can sequence genomes much faster than we could in the past. And this is becoming even faster and faster because the sequencing cost is reducing essentially exponentially with the invention of new technologies. So you can see that in this picture, it's going reducing much faster than the transistor cost is reducing over generations. And as a result, today we can sequence many genomes much more efficiently. The problem is the analyses that we do on these genomes, or that we want to do on these genomes, to understand many different scientific questions. For example, COVID-19 is a prime example today, but there are many other scientific questions in terms of metagenomics, understanding of diseases, understanding of drugs, and predictive health and personalized medicine techniques. We're bottlenecked by how fast we can computationally analyze the data that these sequencing machines generate. And this is a topic that we work on a lot, and I enjoy looking into it. I'm not going to go into it more detail in this talk, but I believe we can enable embedded as well as supercomputing platforms that can do analysis very efficiently in real time if we can actually solve how we can handle the data problem in these machines. You can see a very small machine over here, the Oxford Nanopore machine, in these machines that can sequence genomes very fast. But we have a bottleneck, as you can see. So if you're interested in this, there's a lot of work that's going on in accelerating genome analysis, all aspects of it. And we have recently written this overview paper on it, which is, I believe, a nice introduction to the area. And we also work on accelerators that I'm not going to talk about. This is a near data accelerator that accelerates approximate string matching problems, which is at the core of genome sequence analysis, as well as text analysis. And those are usually hardware, software, co-design. So the future of genome sequencing is very bright. You can see that the technologies are reducing in size and the cost is reducing. But again, we're very much bottlenecked by the computation and the data movement today. And there's more in this. If you're interested, you can watch our lectures like this online. And we also have courses that talk about these. But this is just one example application. I think clearly accelerating genomics is important for many reasons, medical reasons, scientific reasons, and technological reasons. But today, I think we cannot do that easily in real time because our machines are not capable of it. So why? Because data overwhelms modern machines. Modern machines are really not designed to handle data well, in my opinion. Data, as a result, overwhelms the storage and memory capability, communication capability, and computation capability. And it greatly impacts robustness, energy, performance, and cost. So I'm going to talk about why that is the case. If you go back to the first principles of computation, a computing system consists of three key components: computation, communication, storage, and memory. And over decades and decades, more than 70 years, we've fully optimized the computing unit. But we cannot do much in the communication and memory units. Essentially, we can store data, move data, store data, move data, but we cannot do anything to the data in the communication and memory and storage units. And maybe we should really rethink how we do computation in the entire system. We don't want to move data all the way to a processor or an accelerator before we can process it, because that data movement is extremely costly. So basically, we have a processor-centric design in our systems today. And if you look at a processor today, this is my cartoonish picture, because we cannot handle data well, most of the system, even inside a computing chip, is dedicated to components that store and move data: caches, interconnect, other caches, other interconnect, memory controllers, memory, other interconnect, SSDs, tape. So basically, if you look at the system, more than 95% of a single node is really dedicated to storage and movement of data. We call these computing machines, but most of the time and most of the resources, they're not spending on computing, actually. They're doing storage and data movement, essentially. So I think this is an indication of data bottlenecking our performance and energy. But there are other indications. So this is one work that we did with Google 3 years ago. We basically analyzed the workloads that I showed you in the previous picture: machine learning, video processing, browsing. And we found out that more than 60% of the entire system energy on a mobile system is spent solely on data movement, not computation, as you can see. And this shows that data movement is very energy intensive. We'll get back to that. So my axiom going forward in this talk will be that we want to design intelligent architectures because these architectures are going to be making decisions for ourselves that will be affecting our lives in terms of health, in terms of self-driving, in terms of whatever you can think of, in terms of robotics, and they will maybe become personalized. But these architectures should become intelligent as well. Otherwise, we may have significant problems in decision-making as well as energy and performance. So the question is, of course, how do we handle data well? I think there are three major components to this. First of all, we should ensure data does not overwhelm the components we design via intelligent algorithms, via intelligent architectures, and via, more importantly, whole system designs by taking a whole stack approach, algorithm, architecture, devices, whatever layers we have, and co-designing the system end to end so that we ensure that data really does not overwhelm us. Second component is we should probably take advantage of vast amounts of data and metadata that's flowing through the system to improve the architectural and system level decisions we make in the system. Essentially, today's systems are very much human heuristic or human algorithm designed. Humans design the cache policies, humans design the memory controller policies, humans design, I don't know, thread scheduling policies, but maybe the machine itself should be learning and designing itself over time, improving itself over time. So this is data-driven architectures that can learn from their past actions and become better over time. And I think this is also going to be important because there's a lot of amount of data that's flowing through the systems. And the third property, in my opinion, is to understand and exploit properties of different data really well. Because different data that we deal with in our systems have very, very different properties in terms of semantic properties, in terms of algorithmic properties, and in terms of architectural properties. For example, approximability of data. Clearly, different data have different properties. That's a semantic concept that needs to be communicated down into the architecture so that we can actually optimize the system design based on that characteristic. There are other characteristics like security characteristics, privacy characteristics, compressibility characteristics. You can come up with many different characteristics, including locality, for example. But we're not doing well, in my opinion, any of these. And this slide is deconstructing what I said previously, basically. Today's architectures are really not good at dealing with data because they're designed as processor-centric. Everything has to go to the processor or the accelerator so that it can be processed. They're not data-centric. If you were data-centric, you would not move data this much. And we will talk a lot about that in this talk. Second, today's architectures do not take advantage of vast amounts of data and metadata that's flowing through the system. For example, my cell phone, which is 6 years old, has not learned anything from what I have done or what the workloads that I have executed have done or what the environmental conditions have been over the course of these 6 years. It's still executing exactly the same algorithm in its memory control and caches that its human designer dictated it and put into the hardware. And I think this is not acceptable in an intelligent system. If we want to have intelligent systems, we need to give the freedom to these systems to make data-driven decisions, intelligent decisions, as opposed to decisions dictated by a human designer who clearly does not have all the information that the system will see over time, which will be dynamic over the lifetime of the system. I'm not going to talk about that, but I think talk about that in more detail. But I believe designing systems that can self-learn using reinforcement learning or other kinds of machine learning techniques are actually quite promising. And we have some work on memory controllers as well as prefetchers in real systems in hardware, software, co-design related to this. Third property, architectures today are not good at knowing and exploiting different properties of application data. We have all these semantic properties of data. Unfortunately, these semantic properties do not get discovered or conveyed to the architecture in the end. In the end, the architecture is left with ones and zeros, the memory addresses, and very little information about what to do with information about the data. As a result, architectural components make component-aware decisions as opposed to data characteristics-aware decisions. So if we knew, for example, the different reliability or security characteristics of data, you can classify data in terms of error-tolerant or security critical. And you can place this data into special memory chips, for example, that are specifically designed to be reliable and secure. And all of the other data that do not have strict reliability and security guarantees to other memory chips that are designed to be extremely low cost. And we introduced this idea of heterogeneous reliability memory in DSN 2014. I'm not going to go into this, but this is just one example of a data-aware architecture that exploits the semantic information that comes from the programmer or the top and designs the entire system, memory system in this case, so that the memory system is customized for different types of data. And as a result, you get much better, much more scalable memory systems, as we show in this DSN 2014 paper, which I don't show over here. Okay, I've given you examples of data-driven and data-aware architectures. For the rest of the talk, I'm going to focus more on the data-centric architecture paradigm. I also call this memory-centric architectures. So what does it mean to be data-centric? Essentially, today we are very processor-centric. Data has to move to the processor. We want to change that paradigm to be much more data-centric. And there are multiple properties of a data-centric architecture, in my opinion. First of all, you should be able to process data where it resides, where it's produced, where it makes sense, as opposed to having to process the data only in the processor. And this brings us to processing in and near memory structures, as well as communication structures. I'm going to talk about processing in memory quite a bit. But we also want to have low latency and low energy data access. That's important. If we respect data, data access should be low latency, low energy. And there's a lot more work that needs to be done, in my opinion, to have low latency, low energy access to data, large amounts of data, let's say. We want to have low cost data storage and processing, and we want to have intelligent data management. In this talk, I will mostly focus on processing data where it resides, but I'm going to motivate it with intelligent data management, intelligent controllers that need to be handling robustness, security, and cost issues, as I will discuss. But let's jump into it. So I also call this processing data where it makes sense, as opposed to having to process data in the processor. So this is an old idea. Basically, processing in memory, near memory, whatever you would like to call it, has been discussed since 1960s. And this is a very early, beautiful paper written by Harold Stone in 1970, A Logic in Memory Computer. The idea has been revisited many times. It has not panned out. I will argue that today we are in a special position to actually make it happen. Let's take a look at it. Why? Because we have two big pushes. Well, one push from technology. The technology layer at the bottom is asking us to do something very different with memory, to be more intelligent in terms of how we handle memory. And the system level basically application and system level are also pushing us to do something different with memory and our systems. I'm going to cover both of them, but I'm going to first motivate the technology layer. So if you look at the technology layer, DRAM, dynamic random access memory, has been very successful since the 1960s, and we employ it in all of our systems almost. And the problem is it's becoming very difficult to scale it. As a result, industry is open to controllers close to DRAM, new memory architectures. I'm going to talk about these. These are some examples of new memory architectures that people have looked at, and some other examples where you have some little amount of computation of the row buffers of DRAM. But I'm going to give you even more examples from today. These are actually relatively old, but I'm going to jump into 2019 and 2021, talk about in-memory computation devices that are being built by startups as well as companies like Samsung. And but before that, I will give you a perspective until that. So why is this happening? Basically, technology scaling in memory is very difficult. It is becoming very difficult. We're having a lot of issues: reliability issues, retention issues, security issues, vulnerabilities, etc. And this is an early paper that outlines what we were about to see. Of course, other people are also writing papers, but this is one of the papers that we were asked to deliver at the International Memory Workshop. And at that time, we didn't have a lot of evidence, but we were working on evidence in terms of memory technology scaling. This is one evidence. This is basically, we worked with Facebook. Over the course of 1.5 years, we understood the memory errors that they have in all of their data centers. This is a lot of amounts of memory across the entire world, essentially. They have many data centers across the entire world. And we basically discovered a strong correlation between the density of the memory chip that's employed in the server and the error rate that we see in the server. So clearly this is a correlation, but it's a very strong correlation. And the denser memory chips exhibit higher error rates. And this is because as the memory chip becomes denser, cells become closer to each other, they become smaller, and they become more vulnerable to noise effects. As a result, reliability of the memory cells get reduced, and we see it in real systems. And this becomes a cost in a data center because these errors get exposed to the operating system somehow, and you need to correct them. Or you need to use stronger ECC, error correcting codes, which affect your cost. So clearly, as memory scales, it becomes unreliable. And if you're interested, you can take a look at the paper for more detail. We also built a lot of infrastructure. These are smaller, lower level infrastructures to understand such issues. And these are FPGA-based infrastructures. And we could test memory in a fine grain. This is an example of the infrastructure that we have. And we open source this infrastructure. So if people are interested, they can certainly use it, and we'd be happy to support it. So while we were doing a lot of studies in this infrastructure, we found out together with Intel that one can predictably induce errors in most DRAM memory chips. And this is a very scary example of memory technology scaling issues, in my opinion. So this happens because of the DRAM row hammer effect. And we found that this happens in more than 80% of the tested DRAM chips. And this is really the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. And as a result, people like the Wired magazine are writing articles that say, forget software, now hackers are exploiting physics. So this is really a reliability problem that can be exploited like a Byzantine failure for malicious purposes. So what is the problem? Basically, cells are too close to each other. If you look at DRAM memory, it consists of rows. And if you activate one row to be able to read it, you apply high voltage to the word line. It's called opening the row. And if you close the row, you apply low voltage to the word line. And now if you keep doing this repeatedly, open the row, close the row, open, close, high voltage, low voltage, high voltage, low voltage, high voltage, low voltage, high voltage, low voltage, etc. If you do it enough times before the cells in DRAM get refreshed, it turns out you get errors, bit errors in adjacent rows, physically adjacent rows. Note that you're not even writing to memory. You're not even writing to the rows that get bit errors. So this should really not happen. You're breaking memory isolation. And that's why this is not just a reliability problem, but also a security problem. So we call this the hammered row, we call this victim rows, and we have a lot of analyses in our papers. Basically, we show that more than 80% of the chips manufactured by 3 DRAM manufacturers are actually vulnerable to this problem. And this is really a scaling problem because older chips did not have this vulnerability. In 2010, the cells became too close to each other so that you could actually do enough activates within a refresh interval so that you could induce these errors. So this is really a technology scaling problem. Cells are too close to each other. Therefore, there's a lot of electromagnetic coupling that's happening between them. There are also some other effects that I'm not going to go into. You can actually watch our lectures and read the papers that I will flash very quickly. But this is really a technology scaling problem that requires doing something different in our memory controllers and DRAM to fix the issue. And this is a security problem because one can exploit these bit flips because you're breaching memory isolation. The the rows that can get errors can belong to some other process, can belong to the operating system, and someone who is smart and malicious can actually exploit these bit flips to actually induce bit flips in your page table entries so that you can circumvent all the virtual memory protection mechanisms so that you can take over the system. So that's what we envisioned in our paper. Later, Google Project Zero showed that you could actually do it in real systems. And later, there were a lot of work that showed that you could actually take over remote website, essentially, if someone visits a website, you can actually take over that person's computer through JavaScript. You can actually have a malicious app that someone can download, and you can take over someone's phone. You can do it through the remote direct memory access interface. I don't have all the slides over here, but more recently, people have shown that you could actually deplete the intelligence of neural networks, meaning you have a neural network that is reasonably accurate, let's say 90%. It may be used in, I don't know, pedestrian detection in your self-driving car or some other purpose that is life critical. But if someone does a row hammer attack intelligently to this neural network, its accuracy can drop down to 10%. So clearly we have a problem because we're going to rely increasingly more on these neural networks and machine learning techniques. And if they're vulnerable to bit flips in memory, which is really easy to do, as we will also see more, then we cannot rely on anything in our systems, especially for life-critical, safety-critical decisions. But otherwise, also privacy and security becomes a big problem. So that's why these memory technology scaling issues are real, and we need to solve them. And if you're interested in row hammer more, you can read our retrospective. But unfortunately, that retrospective actually doesn't cover something that I will discuss. So how do you solve the problem? Basically, you need to make the memory control more intelligent so that it avoids these problems. I'm not going to go into the details of how you do that, but it requires some amount of intelligence in the memory controllers to understand that this is happening and blocking that. And the control can be inside the DRAM or across in the memory controller. We're not going to go into details of it. But in 2020, this problem is getting worse. We have published some papers that show that newer DRAM chips are much more vulnerable. You can do only 4,800 double-sided hammers and actually induce these bit flips, and existing mitigation mechanisms are not effective. We also showed that mitigation mechanisms that DRAM manufacturers put into the DRAM chips and they advertised as secure, row hammer free, are actually not row hammer free. Basically, in this work, in this trespass work, we show that you can just enough reverse engineer the mitigation mechanisms that are inside the DRAM chips and bypass them, and you're back to square one. You can actually take over the entire system. So it's unfortunate that the problem has not been solved. In my opinion, we have been lacking principled designs for this sort of issues and intelligence in the memory controls, enough intelligence, secure intelligence in the memory controls. That's why that has not been happening. But there are also political issues, of course, clearly. So there's a lot more work in this area in 2020, and we also propose solutions. Again, this is an intelligent controller that solves the problem. I'm not going to go into the details, but if you're interested, you can certainly look at more lectures on row hammer and shorter lectures as well. Okay, so this is one example of the technology scaling dimension, and I think I will harp on it a little bit more. So if you look at infrastructure, we're talking about infrastructure, and computing is probably the most valuable infrastructure, most important infrastructure that we have today. And it's going to be more important because we're going to rely on it in our life-critical decisions, self-driving cars, personalized medicine, life-critical decisions, I don't know, self-flying, many, many things, basically. And we have critical infrastructures like bridges. And humanity has been building bridges for 2,000 years, thousands of years, let's say. And if you get a bit flip in a bridge, clearly it's a safety, reliability, security problem, and we take it seriously. We should take computing infrastructures, bit flips, much, much more seriously because they're going to be much, much more important than any single individual bridge or any single collection of, or the overall collection of all bridges in the world. And clearly, these bridge incidents have fatalities, and you can see there are examples of it. We have not been able to circumvent these and make sure that these bridges are completely fault-free. We need to design systems that are fundamentally secure, basically. We somehow need to design systems that prevent unforeseen consequences. This is an example where people are sitting on a bridge, let's say, a rod, but if you have a bit flip in that road, they will not be very happy in the future. But going into the future, our computing infrastructure is going to be much, much more important than bridges, and we need to take it a lot more seriously than we have taken bridges. But the good news is, to build fundamentally secure, reliable, and safe computing architectures, we need to somehow find ways of predicting and preventing these safety and security issues. We need to be methodical. But the good news is, I think we know the direction. We need intelligent memories. We want patchable memories. And again, the good news is we can do it. Essentially, computing infrastructure is relatively soft compared to bridges, right? If you have reconfigurable or configurable, programmable intelligent memories, you can avoid many, many failures that may come about. Okay, that was the push from technology. Essentially, we want more intelligent memories. Rowhammer is just one example. There are a lot of other issues like reliability, retention, error correction mechanisms that I'm not going to go into, but we have a huge push from technology to make the memory technologies more intelligent. Let me talk about the higher level perspective now, talk about systems and applications. And we see the same thing in systems and applications as well. We have a huge push from them to make our memories more intelligent. Because data access is a major bottleneck, energy consumption is a huge limiter, and data movement energy dominates computation energy today. So basically, in my opinion, there's a huge question we have. Do we want a future that's sustainable, energy efficient, beautiful for our future generations to come? Or do we want a future that is not going to be livable? I think we want the best of both worlds. Essentially, we want energy efficiency and sustainability, no question about that. But we also want high performance so that we can solve the hardest problems that we're tackling going into the future. But the problem is, data access is a huge bottleneck, and our current design principles at the heart of them cause great energy waste and also great performance loss, because we're moving data all around our systems, starting from a single node, from the SSD to memory to the processor, and even within the processor, from the cache to the processing units. We're always moving data. So we're wasting energy. Clearly, we have recognized that this is costly in terms of performance. So we actually put in a lot of techniques to our systems and hardware and software to avoid the performance loss, so that we put a lot of massive levels of multi-threading, massive levels of out-of-order execution, prefetching, multi-level memory hierarchies, etc., many management mechanisms. This mitigates some of the performance loss, not all of it, but it causes even more energy waste, especially when they do not work or they work very little. They cause even more energy waste. They add complexity to the system. So we're in a vicious cycle today. We know what the problem is. It's moving the data. We're trying to mitigate it with patchworks, but that keeps us in the vicious cycle of increasing energy waste, and that's going to spiral into something much bigger going into the future, in my opinion. So we need to fix this. And fixing any vicious cycle requires recognizing what the problem really is. And the problem really is processing of data is performed far away from the data. I need to recognize that, and we need to fix that. And we need to recognize that a real system consists of three components, and computing should not really be done only inside the computing unit. We should not be so processor-centric, basically. Today's processors are, today's computing systems are very processor-centric. As a result, we have all these data bottlenecks that I mentioned earlier. I'm going to give you more examples of this. We know basically the problem. This is Dick Seitz, who was the chief architect of alpha processors in the 1990s. After they designed the flagship alpha processor, which is the fastest of its time, in 1996, he basically wrote an article in Microprocessor Report, one-page article, whose title was, "It's the Memory Stupid." Basically said that we designed this alpha processor. It's capable of finishing 4 instructions every cycle. But in this important database workload, it's finishing 1 instruction every 5 cycles. So it's operating at 1/20th of its peak bandwidth. And he basically said, this is not acceptable. I expect over the coming decade, memory subsystem design will be the only important design issue for microprocessors. That's 1990s. Fast forward to 2000s. This is data from my own PhD thesis, where we showed together with Intel that essentially the same thing is happening on Intel processors, on workloads that these processors are designed for. Most of the time, the processor is waiting for data to come back from memory. And if you're interested, you can actually read the paper also. Now, fast forward 10 more years. This is data from Google showing essentially the same thing on their data center workloads. Basically, the state-of-the-art processor is waiting for data. It's doing computation for a very little amount of time in the screen, as you can see over here. So basically, today's processors are not dealing with data well. They're waiting for data. Because we have a grossly imbalanced system, we dictate that processing should be done in only one place. Everything else just stores and moves data. Data moves a lot. That is the cause of energy efficiency, low performance, and complexity. And as I said, we have overly complex and bloated processors and accelerators, and that increases the energy inefficiency, performance issues, and complexity. And as a result, we're back to the picture that I showed you earlier. Most of the computing systems dedicating to storing and moving data, even though we call the processor computation system, most of the time and most of the resources, it's not, and most of the energy, it's not spending on computation, it's spending on data storage and movement. So let's talk about the energy perspective in a different way. This is data that I borrow from Bill Daly. It's old numbers, but the trends remain the same. So let's take a look at a 64-bit double precision floating point operation, 20 picojoules according to these numbers, and memory read and write, 16 nanojoules. That's 800x difference. So the question is, does it make sense to move data all the way to the processor to do a very small, simple, not energy intensive operation and consume 3 times 800x energy, because you're going to be moving 2 data elements and you're going to be moving the output back into the DRAM. If you cannot exploit locality extremely well, which is really difficult to do in modern workloads and modern hierarchies, it's not a good idea to move the data to the processor chip. Basically, you can argue with these numbers, of course, but it's clear that a memory access consumes at least 2 to 3 orders of magnitude the energy of a complex addition, and that's a simple addition also. So there are other papers that talk about it. I'm not going to go into detail. And we also have done work with Google, as I mentioned earlier. This is the cause of most of the total system energy in important workloads. Most of the total system energy is spent on data movement. Okay, basically, we do not want to move data. This doesn't make sense if you want to be energy efficient, if you want to be high performance, and if you want to be secure and reliable also, but I'm not going to get into that. Basically, we need to have a paradigm shift so that we can enable computation with minimal data movement as much as possible so that we maximize energy efficiency. We want to compute and have the ability to compute where it makes sense, where data is residing, and where data is produced. Basically, we want more data-centric architectures. We want to shift to a data-centric paradigm from the processor-centric paradigm. And memory is one place where computation should be done. There are other places, of course, storage, interconnect, caches. I believe we should really have distributed computation across the system, across all parts of the system. But memory is a special place because people are really designing applications to fit into memory today, like databases, graph processing, media processing, etc., machine learning. And we can take advantage of that. So I'm going to focus on memory in the next remaining part of the talk. Basically, we would like to be able to ask memory, could you please do these operations for me, execute this function for me, execute this application for me, and give me the results. And the memory returns the results. Data moves very little inside the memory. And hopefully, this is much higher performance and much more energy efficient. I'm going to give you some results with this. There are, of course, many, many questions here across the stack. How do we design the memory controllers? How do we design the processor chip and memory units? How do we design the hardware and software interfaces, the system software, compilers, languages, algorithms? And how do we even rethink the theoretical foundations of computing? Because theoretical foundations of computing are processor-centric. Algorithmic complexity theory counts operations. It doesn't consider memory access complexity. It doesn't consider memory capacity. It doesn't consider memory latency. None of this is considered. We just count operations, assuming every single operation is equally costly. That's wrong in today's practical memory bottleneck perspective. Basically, we need to revisit the theoretical foundations of computing so that we can make this data-centric. But we really need to revisit the entire stack of computing, as you can see over here, all the way from algorithms to devices. Okay. So let's talk about processing in memory. Let's talk about 2 approaches to it in the remaining time. I'm going to talk about 2 different approaches, processing using memory and processing near memory. These are fundamentally different. Processing using memory takes a memory device, treats it as a memory device as well as a computation device. Basically, this operational properties of memory cells can also be used to do computation. So they are not just memory cells, they're also computational cells because of the way they're designed. How do we take advantage of that? How do we minimally change the memory device, minimally, so that we can also do computation? Processing near memory is more similar to the current paradigm, where we still have a processor, but we just move it closer to memory. We move it to the memory controller, we move it to the DRAM chip, we move it to the DIMM, we move it to close to the bank, but we add more logic, basically. We're not exploiting the capabilities of the memory array to do computation. So processing using memory is a fundamentally different paradigm, in my opinion. Processing near memory is a closer paradigm to what we are experiencing today, but it's still more data-centric. Okay, let's talk about processing using memory. And let's talk about not even computation, data copy and initialization. Clear data copy and initialization is used in many, many applications, and Google has shown that it's really important. How do we do it today? If you want to copy this white page to the gray page in memory today, we have to go through the processor because we're processor-centric. Processor has to do everything. At least we have to go through the memory controller, which is on the processor chip today, through the DMA engine. So it's clearly high latency, high bandwidth utilization. You cause cache pollution, and you have unwanted data movement. Because imagine that you're doing this copying to do initialization of a 1 terabyte memory. You're not going to reuse any of this. You're basically occupying the memory bus for no reason, essentially. So if you do a 4 kilobyte page copy via the direct memory access engine, it's costly, as you can see, 1,000 nanoseconds, 3.6 microjoules. Can we do better? And the answer is yes. Just use the memory chip to do it internally inside the memory and exploit the operational properties of the memory chip, as I will show you in a little bit. This will be low latency. This will be very high bandwidth internally. This will be low bandwidth utilization and no cache pollution and no unwanted data movement. I'm going to show you a mechanism that takes us 1,000 nanoseconds to 90 nanoseconds and 3.6 microjoules to 0.04 microjoules. And the idea is very simple. At the core of it, you basically have a DRAM array that I showed you earlier. You first activate the source row, which brings the data into the sense amplifiers. You move the data minimally. And then you activate the destination row, which brings the data from the sense amplifiers to the destination cells. Essentially, this happens because of the way memory chip operates, because the sense amplifiers are much stronger than the cells. So by doing 2 consecutive activates, you can actually do this operation very, very fast and very, very energy efficiently with negligible hardware cost. In fact, you can do it in real DRAM chips today by violating the timing parameters of DRAM chips in a real memory controller and real DRAM chips. So it's doable in existing DRAM chips. And the benefits are significant. It's more than an order of magnitude reduction in latency for copying, for a 4 kilobyte copy, a small copy, and more than 70x reduction in memory energy. Of course, you want to do it between banks, between different subarrays, etc. And we have solutions to that I'm not going to talk about because of time constraints. You can read our original paper, and you can read our paper that showed other solutions to data movement inside the memory chip. So you can do it generally, essentially, and you can do it in a fine-grained manner as well. I'm not going to talk about those. And these are the papers that I'm going to flash, if you will. Okay, so basically we're treating memory as an accelerator. We're adding specialized data movement and computation capability inside the memory. I'm going to talk about computation a little bit. Essentially, we can treat memory as an accelerator. Why not? We have a lot of these accelerators all over the system, except they're not in the good place in the system. They're all bottlenecked by the memory bus. Why not have some accelerators on the memory side that is not bottlenecked by the memory bus, that doesn't have huge data movement overheads? And that's the idea, basically. So similarly to what I said, we can do truly in-memory computation. We can do bulk bitwise and or not majority functions at low cost by using analog computation capability of DRAM. And the idea is activating 3 rows concurrently performs computation. And this leads to 30 to 60x performance energy improvement. And you can see that, I'm going to go into this a little bit more detail. You can see that significant applications like databases benefit a lot. And new memory technologies, emerging memory technologies enable even more opportunities, in my opinion. For example, memristors, resistor RAM, phase change memory, STT-M RAM. These are non-volatile. As a result, data movement is even more minimal than DRAM because DRAM is fundamentally destructive reads. But whereas in new memory technologies, essentially you can do the same operations that I described in new memory technologies as well. And you can do more. You can do matrix vector multiplication as well. Of course, you need to design the system to be reliable. So there are some issues over there, but I believe going forward, we're going to solve those issues. Let me talk about how you do in DRAM and in OR. Basically, the idea is triple row activation. If you concurrently activate 3 rows, what you get is the majority function of the 3 cells. Meaning if at least two of these cells are charged, you get the charge state at the end. If at least 2 of these cells are discharged, you get the discharge state at the end. So this is bitwise majority. You can do this across the entire DRAM chip over 8 million bits concurrently at the same time, let's say. Now, you can rewrite this Boolean equation and set C to 1, such that you get the OR of A and B, set C to 0, such that you get the AND of A and B. So you can basically build simple primitives and OR. I'm not going to talk about NOT, but you can also do NOT in our proposal. Once you do that, you can actually redesign your algorithms to take advantage of this Boolean complete circuitry. And if you do that, you can get significant performance improvement. This is the way we designed actually database queries, and we accelerated the bit-weaving database that was designed earlier to maximize bitwise operations. And we see significant performance and latency, end-to-end latency improvements for queries like 4 to 12x. And the performance improvements increased with the size of the data set. Okay, so I'm not going to give you more results, but you can see that it could be very significant. I will point you to some papers that we have written. And more recently, we have been writing programming frameworks that can make this much more general to many applications. I will point you to the SIMDRAM work, for example, but I don't have time to cover it. And we can also do other stuff in memory, like physical unclonable functions. We can generate true random numbers at high throughput, low latency. So we can actually export security functions, security critical applications inside the memory as well. Okay, now let me talk about the second approach to processing in memory very quickly. This is processing near memory. We add logic structures near memory. And if you do that, you can accelerate very important applications. I'm going to give you examples from graph processing. Essentially, graph processing is very important in machine learning frameworks, in bioinformatics, and of course, text, etc., many things. But it's fundamentally bottlenecked by random memory accesses, and it has little amount of computation on vertices. Now, there's an opportunity here. if you have 3D stacked memory, where you have a logic layer underneath memory layers, where you have high bandwidth, low latency connections between this logic layer and memory layers, you can actually accelerate graph processing significantly. And if you have other 2 3-dimensional technologies that may become available in the near future, maybe 5 to 10 years, you can do even more. You can mix logic and memory even better at a tighter integration. So we took advantage of this tight integration of memory and logic, and we designed a graph processing system called Tesseract. It's a distributed system, essentially, that's used like a GPU. You offload your graph computation on this distributed system of cubes. Each cube has logic and memory, 3D stack, essentially. And each logic layer, you have many processors in order cores. These can communicate with each other through a network. And there's also a chip-to-chip network that enables communication. But what we do here is we put the graph nodes, place the graph nodes on the memory. So there's some graph partitioning that needs to be done. And the communication happens just to ship the functions to operate on graph nodes. So we basically don't move the data, we move the processing. And communications are done through remote function calls, and we have some prefetching mechanism. I'm not going to go into the details of it since it's a full system design. But if you're interested, you can certainly read the paper. I'm going to give you results. So if you design a system like this, it's different from any other system that we have today. Today's systems are processor-memory dichotomy, but Tesseract looks like this. Basically, processor and memory are together. As a result, you get 8 terabytes per second exposed by 2015's standards, actually 2013 standards, whereas no other system can reach that between processor and memory in 2-dimensional integration technologies. And the result in terms of end-to-end application performance is significant. We can basically get almost 14x performance improvement. Later research actually improved this even more. They basically show that you can get 2 orders of magnitude improvements. And energy is commensurate also. You get basically more than 8x. Again, later research that built on our research showed that you can get close to 2 orders of magnitude energy reduction. And I will point you to paper for more details. Let me very quickly talk about this limited form of this. We analyzed consumer devices and consumer applications like this, as you can see on your screen: video playback, capture, machine learning, browsing. And we found out, as I said, more than 60% is spent on data movement. And together with Google, we wanted to understand the potential of processing in memory in these applications. And we basically observed that often data movement comes from simple functions. We didn't want to redesign the entire system like we did for the graph processing, but we wanted to offload these simple functions to memory to special low-power cores or small fixed function accelerators or some reconfigurable logic, which I'm not going to discuss. But if offloading the important functions actually lead to significant performance energy improvements, as you can see over here, 2.3x and 2.2x. And we didn't optimize the system significantly in this case. So you can see that there are important functions in TensorFlow Mobile are data intensive, packing, unpacking, and quantization. And these are very good fits for processing in memory. I'm not going to go more into detail because we don't have much time left. But I will say that you can do this with any system. You can have a GPU in the logic layer of 3D stacked memory and do truly distributed processing in the GPU. You need to, of course, partition your code. You can do it for linked data structures. You can do it for dependent cache misses. You can do it for prefetching accesses. You can do it for climate modeling, as we do it with the FPGA and HBM-based memories. We could do it for approximate string matching. You could do it for time series analysis. So many applications can benefit from this near memory acceleration. And to be able to do this, I believe we need to revisit the entire stack, but we can get there step by step. So if you're interested more in processing in memory, we have recently written this overview paper that touches into a lot of issues in processing in memory, and we have other stuff also. Now, the good news is there are real companies that are doing real systems. So this is the UpMem startup in France, whom we work with, and they have actually put processing units inside the DRAM chip, and they have built these DIMMs, and we have been using these DIMMs in our lab. And if you're interested, you can watch our recent lectures that talk about our results in this UpMem PIM engine, which we show that in workloads that are suitable, this is much higher performance and much lower energy compared to existing CPUs and GPUs, because you have processing units, simple pipelines next to the DRAM bank. Now, more recent, you can of course have FPGA-based near memory acceleration of data-intensive applications. We look at genomics as well as climate modeling in this case. I'm not going to talk about that more. But Samsung more recently introduced function in memory DRAM where they can accelerate matrix operations, essentially multiply and accumulate operations. I shouldn't say matrix operations, multiply and accumulate operations with simple units near DRAM bank, similarly to what we have been talking about essentially. I'm not going to go into more detail, but you can take a look at more detailed lectures on processing in memory, and we have tutorials on processing in memory as well, if you're interested. So that brings me almost to the conclusion. Essentially, we want fundamentally energy efficient architectures that requires us to be data-centric, in my opinion. Fundamentally, high-performance architectures also requires us to be data-centric. And I believe fundamentally reliable and secure architectures also require us to be more data-centric. So we want such data-centric architectures that minimize data movement. So clearly there are adoption issues I'm not going to cover in this talk, but there are many, many adoption issues, but we need to change our mindset from process-centric to data-centric so that we can start solving those issues one by one. Software, programming, system support, coherence, virtual memory, runtime systems, compilation, access and sharing control, security, privacy, infrastructure success benefits, all may look like a mountain if you have a process-centric mindset. If your mindset is different, you can solve those problems. Okay, so we need to revisit the entire stack, but we can get there step by step. So we have some papers that try to get there step by step, as you can see in this work. I'm not going to talk about these. And I believe PIM, processing in memory, can enable new medical platforms, as we discussed earlier. That's why we are working on PIM and genome analysis together as well. Okay, so what we do not have time for in this talk is fundamentally data-driven, self-optimizing computing architectures. I mentioned them briefly. And fundamentally data-aware, more expressive computing architectures where you have semantic information about data communicate to the architecture and the system so that you can make much better decisions. If you're interested in this, there's more info we have on our lectures and in this tutorial that I delivered at IEDM 66. Okay, let me conclude very quickly. So I've talked about all of this. Architectures today are not dealing well with data, and I believe we need to be more data-centric, data-driven, and data-aware to deal with data better. And it's time to design more principled system architectures to solve the data problem that we're experiencing. We want to design complete systems to be truly balanced, high performance, energy efficient, and that requires us to be more intelligent in our architectures, which in turn requires us to be, in my opinion, to be data-centric, data-driven, and data-aware. And we want to enable computation capability inside and close to memory especially. This can lead to orders of magnitude improvements, enable new application and computing platforms, enable better understanding of nature, and who knows what else. And with this, maybe we can approximate or do better than nature going into the future. But we need to change our minds so that we can have open minds to exploit and discover new principles. So with that, I will conclude. If you're interested, there's certainly more we have. I will acknowledge people who received funding from. Please keep funding us, continue. And I will acknowledge especially my students and collaborators in our research group. And you can see many of them here. You can read our newsletters if you're interested. And you can find all the information, papers, talks, and artifacts, source code on our websites. Thank you very much. I'm happy to take questions.
Thank you, Onur. The very great talk. So this is for the Q&A. We have a couple of minutes for the Q&A, but then so far, I don't see any in advance question. Okay, here is one from Addison. So can you see that question chat or not?
I cannot see it, no.
Okay,
I opened the chat.
So
but, yeah.
I will read. Okay, I will read. So the first question is, can we get a copy of Onur's? So maybe the slide is available later, I think. So there, okay, the question from the Marek, and it is not related to the fact that the memory engineers and the trained and the work separately from processor engineering. So memory engineers and the processor engineering are separated. So
yeah, exactly. I think that's part of a cultural problem also. Yes, absolutely. I agree that that's part of the problem. Memory and processing engineers are trained differently. They think of themselves as memory people versus processor people, right? I think we need to bridge that gap and have a better mindset, make people working together. And I think education has an important role to play here. We need to educate our engineers to be more across the stack, let's say, as opposed to compartmentalize them. So I think we want problem-focused engineers as opposed to compartmentalized engineers.
Okay. So the next question is that from the Jan Piotrowski, and maybe he said maybe he's wrong, but system capable of the universal in-memory processing like the one you proposed could potentially take over current version of the Ethereum blockchain since it is based on the memory hard proof of work algorithm.
Okay.
So, is it good for the blockchain problem?
I see. So I mean, potentially, right. I think I have not examined personally the blockchain problem, but yes, it will reduce the data movement that happens in blockchain and analysis and algorithms. So I think someone who is experienced in the algorithm should look into it. But I believe that system, yes, is capable of doing anything as long as you design the algorithm for it. And yes, I think you will gain benefits. We saw a lot of benefits for many algorithms that are data intensive that we have more experience in.
Okay, so next one from Steve Leak. What things should accelerator programming models like an OpenMP take into the consideration to support these new developments? So programming model for the PIM.
Yeah, that's a great question. Actually, I think near memory computation and processing using memory are different from this perspective. But we do need some primitives to enable, at least to begin with, the programmer to offload code to a near memory computation engine to specify that, okay, this should be probably executed in a near memory engine or a processing using memory engine. And I believe if you look at, for example, UpMem software development kit, they do things like this. So UpMem is a company, they already have a software development kit, and they change the programming model so that they can enable this sort of offloading. And I think that's true for OpenMP and any kind of programming paradigm that aims to support the data-centric systems.
Okay, so we have two more questions. Maybe this is a last chance with these two questions. So the first one out of two is from the Jarosław Skomia. Would in-network computing be a good extension of your approach? So you're talking about in-memory computing.
Sure. Yeah, absolutely. I think certainly, yes. I think in-memory computing is a good example, but I think there should be computation done in-network while the data moves or in the routers, also in the storage as well, in SSDs. I believe we need to have computation wherever data resides and moves, and we need to be able to partition our workloads so that we can take advantage of that distributed computation capability across the system.
Okay, so the last question is from Shahid Boraringwa. I'm sorry for the bad pronunciation. So the RISC-V is growing beyond just an open ISA. So do you think that we can use this to help solve some of the adoption problems?
Yeah, absolutely. I think so. I think open ISAs that we can easily change and add instructions to so that we can support processing near data. And in fact, we actually have some work that is going on right now in the RISC-V. But I think if people are excited about this, I think that's a great way of solving the adoption problems in the hardware side as well as the system software side, because you can run real workloads without being chained to ISAs that you cannot change.
Okay, so this is the end of the question queue, but just one question, please allow me. So I'm very curious that the combination of the traditional von Neumann system and your PIM-like approach, because PIM-like approach, of course, have some limitation. For example, the capacity of the memory bit. So the goodness of the von Neumann architecture is that we can extend the memory capacity as much as we can have energy and space. But for example, in the high performance computing, we must handle the really large scale data and also on the multiple memory devices where we need to move the data because data is not perfectly localized in the one memory chip. So I think that maybe the future system, we have several different part of the still von Neumann and your PIM and something else to apply these things for the vice versa for the characteristics of the computation.
Yeah, absolutely. I agree. I mean, I don't mean. Yeah, I understand your question. Thank you. I think absolutely, I agree with you. A data-centric paradigm, I don't think can completely replace the processor-centric paradigm, let's say. I think they need to coexist and live together, and because they are fit for different types of computation, right? In fact, I don't think a data-centric PIM processing and memory system can beat an existing processor today if your data is nicely fitting in your caches, for example. It works really well, I think, and it's very hard to beat that. But yes, I think if your data is also very large, you need some sort of control components that enable you to actually manage the data movement, and that I think requires us to use more, let's say, von Neumann or processor-centric systems. So absolutely, I think heterogeneity is the future, and maybe there are some other paradigms that need to be discovered as well.
Okay, thank you very much. So we are sorry, but our time is ran up. So thank you very much, Onur.
Okay, thank you very much. I appreciate it.
Thank you.
Yeah.